IAP period. Glad to see such a great turnout, and there are a couple of seats up front here, and I think on your left side as you come down front if you want to grab a seat. I'll point out, if you didn't see it already, there's a handout in the back of Energy Futures Week. On the back side of it, there's a listing of events, energy events during this week. So please grab one. If you didn't get one on your way in, there'll be copies there on the way out that you can pick up. It's a real pleasure to have, as a kickoff event, a lecture this morning by Don Sadoway. Professor Sadoway has been at MIT since 1977, where he is the John F. Elliott Professor of Materials Chemistry in the Department of Materials Science and Engineering. He does research on a wide variety of topics, and many that are very relevant to today's new awakening to the energy needs of this country and the world. But he's focused for a long time on the scientific underpinnings for technologies that make and efficiently use energy. He's particularly well known around MIT as a great teacher. He's well known as the lecturer in 3091, the solid state chemistry subject taught in material science and one of the Institute chemistry subjects. For that outstanding teaching, he was elected a McVicker Fellow in 1995, and he received the Bose Award in teaching from the School of Engineering in 1997. So the highest teaching awards from the Institute broadly and from the School of Engineering in particular. Don grew up near Toronto, and he received all of his degrees in engineering science and in chemical metallurgy from the University of Toronto, bachelor's, master's, and PhD. This morning he's going to talk to us about some of his recent work on high-performance rechargeable batteries for sustainable transportation and large-scale storage of electric power. As I think you'll see, so he has, I think, maybe the most innovative ideas in storage technologies out there. And one recognition of that was in the first round of the newly created ARPA-E program at DOE. They received some 3,700 proposals for their solicitation of, I don't know, I think they awarded 30-something awards total. In the overall ranking of those 3,700 proposals, Don's was first, which I think says a lot about the view of the scientific community about what he's doing in novel thinking in this area. So Don, welcome, and it's a pleasure to have you. There's one more seat down there and two more down here. You want to grab a seat?
Well, thank you, Bob, for the kind words of introduction. Thanks to all of you for coming to this first event of the Energy Week. So what I'm going to do is give you some commentary of a general nature at the beginning, and then I'm going to dig down a little bit and talk about the battery for storage of large-scale electrical energy. So first thing I want to say is that we need to think about different approaches for different applications. There's no single best battery chemistry. You have to know what the battery's for. Number one, don't pay for attributes you don't need. And it's very much economics here. And I know that here at the university we like to get excited about the science. And don't mistake me, that the science is important. Without the science you can't invent. But if it's not cheap, it doesn't matter. Paper in nature, cover art in nature doesn't make any difference if it isn't cost effective, and that's what's limiting batteries. So don't pay for attributes. Pay is the operative word. Cell phone needs to be idiot proof. It goes in the hands of the consumer, and if somebody misuses that device, you can get sued. You have to make you have to take steps to make sure that even the greatest misuse of that phone can't result in injury. The car needs to be crash-worthy. And so you just can't take a whole bunch of cell phone batteries and string them together and put them in a car, because the likelihood of a collision means that you have to take more pains to make that car crash-worthy, which means the cost of the device goes up. Safety is a premium. You bet the company. We live in a litigious society. If there's an accident, we never blame ourselves. We blame somebody else. And what about service temperature? If there's no human contact, it doesn't have to stay at room temperature. You can use a high-temperature battery if you're not putting it to your face or you're not sitting on it. And last comment, stationary batteries, you have much more freedom and choice of chemistry. That's the good news. The bad news is very, very low price point. And what are the price points? Well, when you buy a battery for a laptop computer, you pay about $2,000 to $3,000 a kilowatt hour. It only costs you a couple of $100, but take a look. It's on the back of the battery. It tells you how many amp hours. You know what the voltage is. You figure it out. It's astonishing. For a cell phone, it's about $1,000 a kilowatt hour. For automotive traction, the price point is $100 a kilowatt hour. I mean, if I gave you the lithium for free, if the workers worked for free, you still couldn't reach that price point with today's technology. And this is the killer. For stationary storage, it's $50 a kilowatt hour. And you know why? Because you're not competing against a battery. You're competing against a gas-fired peaking unit. And whenever you put a battery in a competition with hydrocarbon combustion wins every time. That's why we use hydrocarbon fuels, because they're so darn good. Now, the severity of service conditions increases from top to bottom. Any fool can make a laptop computer battery, and a lot of fools are making laptop computer batteries and making a lot of money doing so. Down here, it's very difficult. These are very, very demanding performance conditions, and the price point goes in the opposite direction. So if you started a battery company, would you start a battery company to make batteries for stationary storage? No. But where's the societal need? It's here. Societal need is here. It's not here. So what are the misconceptions about batteries? You know, for years I've worked in electrochemistry. There was a time when I'd walk down the infinite corridor with a paper bag over my head because people said, "You work in electrochemistry? You want to work on batteries? Isn't that kind of 19th century?" So now we're in the wireless age and everybody's running around looking for power. You see people in airports running around looking for those things because it's all about the battery. People say not much has changed. That's not true. Batteries have changed enormously over the years. There's no Moore's law here. The reason is, if you knew what Moore's law is all about, it's just a scaling law. It just means that we're able to get lithographic dimensions finer and finer. It's the same chemistry. We're still building the same chip out of the same materials, only we're getting the features finer and finer. If you want to invent a new battery, that's a new chemistry. We're still on the same chemistry in microelectronics that we were 40 years ago, and that's not condemnatory. It simply explains why we have the luxury of Moore's law, and I'm all in favor of Moore's law. But I bristle a little bit when people look at me and say, "How come there's no Moore's law for batteries?" It's because you got two interfacial reactions involving electron transfers at an interface, and you got to transport mass. You're not just moving electrons from a conduction band to the valence band. It's difficult. But there's good news. There's plenty of room at the top. Feynman said there's plenty of room at the bottom. I said there's plenty of room at the top. We're not up against any natural laws. And if we make the investment, we will invent new battery chemistries. We don't need to have light move at 10 times its current speed in order to enable what I'm talking about. We haven't hit the limits yet. And one of my themes is we've got to start thinking beyond lithium. Lithium is today. That means it's in the past. If you can buy it in a store, it's in the past. And the field is woefully underfunded. In 2006, energy research in total in this country was about $1.4 billion. And that's 1/6 of what we were spending in 1979 if you adjust for the change in the value of the dollar. So from 79, which was sort of the end of the Carter presidency after the 1973 oil shock, we were investing heavily in energy research. And if you take the number we had in current dollars, we're down about, divide by 6 or more. And meanwhile, medical research is written by 4x over that same period of time. So it's not as though, you know, just get over it, research funding got tight, so on. So if we think that energy is a priority, then we have to start spending as though it's a priority. And there have been some hopeful signs recently, but we got a long way to go. So how do you accelerate the rate of discovery? Well, we need more money. It's quite simple. There's no magic there. If you got more money, you'll get more people. People will stay in the field. If you're a young person, you're bright, you're thinking about a career, you know, if you go into the life sciences, you can look forward to 30 years of uninterrupted funding, good funding. I was reading in the New York Times about 2 years ago, somebody was lamenting, it was a professor in some life science field saying, it's so tough to get grants now, the chances of success are 1 in 3. 1 in 3! And you know, Professor Armstrong just gave you the statistics, and this is ARPA-E, the new ARPA-E that's going to charge forward 3,700 concept papers, 37 grants. By my math, that's 1 in 100. So, 1 in 3, 1 in 100. What are your chances of getting tenure when your chances of getting a grant are 1 in 100? You wonder why people aren't flocking to the field. We've got to spend more money. We need new approaches. It's not just, you know, I think I'm smarter than the other guys. I'm not smarter than the other guys. But we can stand on each other's shoulders, and then we've got to bring new tools in. Thanks to the microelectronics revolution, we have computational power on our desks that rival what supercomputers were doing 20 years ago. So let's get Schrödinger to meet Volta, and let's use the computational power of quantum mechanics and start designing materials, and then take the small, high likelihood candidates and go into the lab with those. We've got to conserve resources. You can't just put lots of people and carpet bomb the periodic table. It's too big. There's too many variables. And there's not enough time. Put enough monkeys with enough typewriters, you think you'll come up with a Shakespearean sonnet. But, you know, we got to solve these problems soon. And by the way, confine the chemistry to earth-abundant elements that are readily available. It makes no sense to trade in dependence on imported petroleum for dependence on imported lithium. I mean, we have to make batteries how cheap? We have to make them dirt cheap. And how do you make them dirt cheap? You make them out of dirt. And you make them out of American dirt. That's what you do. This is the design problem. I walk in with a bag of American dirt. I put it on the table and I say, the battery will be made of elements contained in this bag. Not, oh, I listened to a talk a little while ago, I won't name names, it was on this campus, only on a university campus, and somebody was talking about fuel cell electrodes, and they were going to replace platinum with gadolinium cerium oxide. Well, I don't care if that thing's 100%. I said, what are you going to put that in a car? Gadolinium cerium oxide? Take the mass of a car, divide that into the cost of the car, and you pretty much figure out that if it's more than about $2 a pound, it's not going into a car. So we need to keep that in mind at the beginning of the discovery, not invent something that costs $200 a gram and then wave our hands and say if we build enough of them, the price will go down. Do you think if the world demand for platinum goes up by a factor of 100, the price of platinum is going to fall? No Moore's law. All right, so we're going to talk about stationary batteries for storage and delivery of off-peak power. So this is capturing the lost energy in the wee hours of the morning and enabling renewables. That's the problem with renewables. The wind doesn't blow all the time. The sun axiomatically shines in the day. How do you draw electricity from the sun when the sun doesn't shine? Because if you can't, then no one's going to install that because they're going to need a backup unit. And what are they going to use for a backup unit? A hydrocarbon-fired combustor. So there goes your green seal of approval. There's only one reason. Suppose I gave you 100% conversion efficiency on your photovoltaics. What happens when the sun doesn't shine? You got no answer. That's the answer. It's storage. It allows you to draw current from the sun when the sun is no longer shining. If you can't do that, no one's going to adopt that technology. And then powering electric vehicles, that's the tough one. And the gambit there is petroleum displacement. So let's go back to the first one, low-cost, high-amperage storage, grid power load leveling, and uninterruptible power supply for manufacturing plants, hospitals, you name the scale. This is what we need. And again, you can't take a bunch of cell phone batteries and string them together. Too costly and unsafe. So there's only one existing technology. If you really wanted to dig deeper and say, is there no battery out there? There's one. But remember, this is not the competition. This is the state of the art. The competition is the gas-fired peaking unit, because they're cheap. I mean, it's just basically a can with a nozzle. So it's a sodium-sulfur battery. It was invented in the United States and, of course, abandoned. And now it's being produced by a Japanese company, NGK. Some of you car buffs might know the NGK spark plugs. It's a Japanese company, of course. It's a big company. It's got many divisions. And so here it is. It's sodium liquid is the anode. Sulfur liquid is the cathode. So normally a battery has solid electrodes and a liquid electrolyte. This battery has liquid electrodes and a solid electrolyte. So the solid electrolyte is beta alumina, which is a sodium ion conductor. So on discharge, sodium wants to react with sulfur to make sodium sulfide. But it can't do so because they're separated, so it has to undergo electron transfer reactions. That's how you build a battery. So sodium turns into sodium ion on the anode and dumps an electron on the anode, and then the sodium goes across the beta alumina to the cathode, and then to the cathode it picks up an electron and reacts to form sodium sulfide. So this is what it looks like. This is the blue is the liquid sodium, and then you've got a closed one-end tube made of beta alumina, and then the outside, the yellow part, is the molten sulfur. But the solid electrolyte makes this design unscalable. If it's not scalable, it's not going to be cheap. So if I want to make a battery big enough to run a laptop, I can have a battery about this big, right? You're just looking at me saying, that's a stupid form factor. That's your form factor because you have to make a closed one-end U-shaped tube out of a ceramic. And that means it's going to be about the size of a soda can. You can make them smaller, but you can't make them bigger. If I want a battery that's going to have a capacity of some hundreds of amp hours, thousands of amp hours, you say, well, why don't you just make a closed one-end tube? Instead, the length bar here could be a meter. The trouble is you can't make a closed one-end tube out of aluminum oxide that's paper thin, the size of a 33-gallon garbage can, because it's a ceramic. And ceramics have fine qualities, but mechanical strength isn't one of them. You say, well, just make it thicker. Well, if you make it thicker, then the resistance across here is so high you can't get current out. You'll have a voltage penalty. So that's the end of the game. If you want to have high capacity, you take hundreds of these and you string them together. So what's that do to scalability? Your manufacturing cost just went way up and will always be way up unless you find a place on the planet where people will work for nothing. So this is taken from the NGK website. See this? That's this. That's all these little cells. Hundreds of them. If you look at the size of this, it's a little bit smaller than that, but you know, it's solid electrolyte. That's the problem. And this is from the New York Times about American Electric Power is now signing an agreement with NGK, and they're going to start using these batteries for wind power. They're expensive, they're impractical, but people just want to get on with it to see what would happen if we had batteries. And then, in fact, forget about the fact we can't afford them. Just let's get down the learning curve, and then maybe somebody will invent a better battery. So this is it. If we really do get cheap storage, that's a game changer. That's the quote. So now I'm going to tell you what we're doing, the project that Bob Armstrong mentioned. So, and I want people to understand how we got there. I think the genesis of the idea is fun. The idea, once you see it, okay, whatever. But how do we get there? Well, for me, it's about asking the right question. Isn't that what education is supposed to do? It's not providing answers. It's to teach you how to think about the problem. If you ask the right question, the answer is obvious. So we had to pose the right question. Now, you know, batteries are current sources. You might think of a battery as voltage. Now forget, voltage is like water pressure. A hose doesn't deliver pressure, it delivers water. And the measure of water is the current flow, the water flow. Whether it flows at 10 psi or 20 psi doesn't, it doesn't make any difference. It's the water flow. It's electrons in motion, it's current. So the battery will store charge, but it doesn't like high currents. You don't like to shove high currents into a battery, and if you try to draw super high currents, you'll just polarize it and the voltage plummets, and that's the end. So everybody's trying to figure out how to teach a battery to handle high current. So we turned a problem around. Instead we said, why don't we find something that intrinsically loves to handle high current and teach it how to store charge? Well, as Bob mentioned in his introduction, I've been working on electrochemistry ever since I came to MIT, and I started working on batteries in the mid-90s. Up until then, and to this day still, the other half of my research is on the use of electricity in materials processing, in particular how to make metal, how to make tonnage metal. All the world's aluminum, 40 million tons a year, is produced by an electrolytic process where you draw current and you decompose aluminum oxide into liquid aluminum, and with the assistance of carbon on the anode, you make carbon dioxide. So then you make magnesium by electrolysis, and you make sodium, and you make lithium, and you make a lot of the reactive metals that can't be reduced by carbon. You use the electron as the reducing agent. So I know how to use current. I know how to use current efficiently. I know how to waste current. Talk to me. I can waste current for you. So I said, well, what if I found a giant current sink and then taught it how to store charge? So what's the biggest current sink I know? An aluminum pot line. This is an aluminum smelter. What you're looking at, these are all the aluminum cells like this. And each one of these iron posts leads to a carbon anode. And so there's all liquid here. 500,000 amps, 4 volts. That's a pretty good battery. Right? Now that's on drain. That's charging the battery. That's taking current down. Now if I could just convert that into that, we'd have the answer to our problems. And that's the genesis of the project. Right? So first of all, I said, well, why is an aluminum smelter not a battery? Maybe the aluminum industry's been missing this the whole time. So let's look at what goes on inside that cell. So here's the carbon anode. See this steel post? That's this thing. Here is a big block of carbon. This is about 1 meter across. This is not to scale. This orange zone is the molten salt electrolyte. It's running at about 960 degrees centigrade. And we're passing current, making liquid aluminum here, and carbon dioxide. The aluminum oxide reacts with the carbon. You get carbon dioxide here, aluminum here, and the carbon dioxide bubbles away. So I said, oh, that's it. It's fugitive. If I could trap the two products of the electrolysis, have them available for the return journey, then I'd get the carbon dioxide want to re-react with the aluminum, and I'd have a battery, except this is a gas. Even if I put it under pressure, it's no good. It's dielectric. It doesn't carry current. It's no good. What you need is to produce liquid metals at both electrodes. Well, that sounds straightforward, because now you got metal here and a metal here, and you got conductor, moving interface, and so on. Now, let's do some basic chemistry. Any compound consists of a metal and a non-metal. You break it into the metal and the non-metal. And then if you want to reverse the journey, there's the metal cation. With electron, you go to metal. Any fool can do that. That's called dog bites man, right? Now, this is the anion. The anion, convert that to a liquid plus electron. That's different. That's called man bites dog. That's not. You don't make metal at the anode. That's where you make the gas. But that's what we have to do in the same place at the same time. So, as Bob mentioned, I teach 3091. It's freshman chemistry. Everything you need to know is right here. So here's where the metals live. It's about 75% of the periodic table. Here's where the nonmetals live. So if you take calcium plus chlorine, you got calcium chloride, magnesium plus oxygen, magnesium oxide, and so on. Good electron donor, good electron acceptor. What about here? You see this staircase? You zoom in on that staircase. Here's the staircase. There's the metals over here, there's the nonmetals over here, but it's not an abrupt transition. So if I took antimony by itself is just a plain old metal. It's shiny, it's ductile, it conducts electrons. But if I take antimony and I put it in the presence of a really good metal, magnesium, and how do I know it's a really good metal? I look at the electronegativity. Electronegativity, magnesium's down at 1.3. It's a really good electron donor. Antimony is an electronic conductor, but its electronegativity is 2.05. So if you put antimony in the presence of magnesium, guess what happens? Magnesium intimidates antimony into becoming an electron acceptor. And so antimony behaves as a non-metal. It will form anions. Same with arsenic, same with tellurium, all the ones along here. So now, I want to try this out in practice, but I need money. So what am I going to do? Write a research proposal to the DOE with a chance of 1 in 100? I'm not wasting my time. Fortunately, at MIT, we had the Deshpande Center. Still do. And so we got some in-house funds to try this idea out, subsequently with the Chesonis Foundation. This was before the MIT Energy Initiative. The MIT Energy Initiative had been in existence. That would have been my first place to apply. So here's the concept. Magnesium's a liquid. It's a liquid metal. It's got a density of less than 2. Antimony's a metal. It's got a density greater than 6. And the molten electrolyte, molten salts are about 3. It self-orders. There's no solid membrane. There's no solid separator. So on charge, all I do is decompose the electrolyte, make magnesium at the cathode and antimony at the anode. On discharge, magnesium wants to react with antimony and does so by shedding electrons which go through the external circuit over to the antimony. So this is a liquid metal battery. It's 3 liquid layers. We've moved way beyond this, but this is what I'll talk about in public. So I know all the criticisms of it, but we made it work and demonstrated the concept. So we called it reversible ambipolar electrolysis because we're making metal, liquid metal, cathodically and anodically. And in fact, one of the claims in the patent on this is the production of metal by anodic deposition. Normally, if you anodize, you think of, if you anodize aluminum, you make aluminum oxide on aluminum. Now, we're making metal, certain metal. So here's some, we don't just put stuff together and cook and look. My students have to get PhDs, for heaven's sake, so they have to do something academic, right? So this is the basis. This is voltammetry. This is the current voltage characteristic of an electrode. So this is, if you start with the red line is just molten zinc chloride. And so this is the current axis, and this is voltage. So as you go cathodically, you go out, out, out. There's no current over a certain range of voltage. The system's behaving as a capacitor. There's no Faradaic reaction. And then you get out to a critical value of potential, and it's just beyond the 0 because we're using zinc as the reference electrode. So zinc versus zinc should be 0. As you get just a little more cathodic, you see the current rise. That's zinc deposition. So as zinc comes out of solution, you get a current. And then we reverse the current, and you see this wave here? That's the stripping of the zinc that you just deposited. So we're demonstrating the reversible deposition and stripping of zinc. And then you go out in the anodic direction, nothing, nothing, nothing. If you go really far out, we'll start to decompose and make chlorine gas. But I just want you to see that the red line does nothing. Now we add zinc telluride. Remember, tellurium is one of those elements on the staircase. And now we go out in the cathodic direction, we make zinc and strip zinc. We go in the anodic direction, and in the anodic direction we have a wave, and that's the deposition of tellurium, and that's the stripping of tellurium. This is the ambipolar electrodeposition. In the same cell, we can make liquid zinc and liquid tellurium. That's different. Liquid tellurium. All right, so this is what it looks like. Here's a scale. There's the human indicator. This isn't a giant. This is one of us, and you can see the dimension. This is on the order of about 1 inch in diameter. So we've got anode metal, salt, cathode metal, and all of this hardware put together. And we have to heat this by external means using electric furnace. But at full scale, the thing is self-heating. Aluminum cell, you don't heat it. People say, how are you going to get to 700 degrees? Magnesium melts at 650. How are you going to get to 700 degrees? The current. What happens when you ever put it's called a laptop? It should be called the unlaptop. Don't put the laptop on your lap, okay? It gets warm, doesn't it? It gets warm on charge, and it gets warm on discharge. Current across that electrolyte generates joule heat, and that's how you keep the cell at temperature. You cool an aluminum cell. You cool an aluminum cell. Anyway, so this is the scale. This is what it looks like in my laboratory in the beautiful bowels of building 4. 4, yeah. All right, so here's a furnace, and we've got this thing in a furnace. This is just a Canthal wound furnace. This is electrochemical testing stuff, and there's charge, discharge curves, et cetera, et cetera. So here's one of these things after cycling. So you can see that the liquid metal has formed here and floated on the top. This is the solidified, previously molten salt, and this is the second metal. And what we've got in here is a boron nitride spacer, because in an ideal cell, you have an electrode coming in from the top and an electrode coming up from the bottom. But we need a crucible in this cell. And so we use the crucible as the electrical contact for the lower electrode. So we have current coming like this across the electrolyte up here. And this liquid metal will short to the side. So we've got boron nitride spacers in there. But in the full-scale cell, you know how you run a Hall cell or an aluminum cell? You run it at elevated temperature, and you bleed heat out the sides, and you freeze salt against the sidewall. So your containment problem is gone. It's all about thermal management. It's not an isothermal system. If it were, you could never make it work. But in the lab, most people have a scale-up problem. We have a scale-down problem. I hate working with the tiny cells. So there's the electropositive anode, molten salt, electronegative. So what are the attributes of this thing? Very, very fast kinetics, because it's just liquid to liquid. Magnesium ion takes 2 electrons, becomes liquid magnesium. No change of phase. No electrocrystallization, no gas bubble generation evolution. The activation voltage is next to 0. And you don't have any diffusion. You know, a lithium-ion battery, the lithium gets across the electrolyte and it's got to go deep inside the intercalation compound. This thing here, it's a moving interface. So you just make it rise, and then when you discharge, you just watch it fall. There's no wasted time, wasted effort diffusing in and out. No solid state diffusion. And we think that could lead to long service life, because most of the breakdown mechanisms of a lithium-ion battery involve the volume excursions and so on that go on inside the electrodes. And when did you ever think in a battery talk you'd hear the word self-assembling? That's hipster, modern, cheechy material science. But this is self-assembling. There's density. You have density and immiscibility. Liquid metals don't dissolve in molten salts, and then I have them self-assembled. And of course, there's some electrochemical requirements, and there it is. So it's scalable at low cost. If I want to, I've made the small ones. They're smaller than this soda can. If I want to make a battery the size of this area that I'm standing in, I mean, this is the way an aluminum cell is made. They don't take hundreds of these. They just fill this. Imagine this filled all here up to the depth of my knees with molten antimony, then about 2-3 inches thick of molten salt, and then up to my waist with molten magnesium. Now, how much charge we can store in that footprint? It's phenomenal. You know what the current densities are in this thing? You know, a lithium-ion battery, it's tens of milliamps per square centimeter? It's nothing. You know what the density is in an aluminum cell? 1 amp per square centimeter. You know what we measured in our single electrode experiments? 100 amps per square centimeter. Phenomenal. That's a small footprint, and that leads to cost reductions. If it's not cheap, who cares? We've got enough of the other stuff. That's boutique science. All right, so this is some charge-discharge curves, it cycles. Yeah, some recognition. Yeah, this is the cartoon from Technology Review. There it is. Okay, and then we got the ARPA-E grant, which we're enormously thankful for, because now we can really dig in. So the ARPA-E grant is designed to take this from the size of the soda can to, we call it Electroville, the size of a substation. Size of a substation. So we've got to get busy. So I've got to hurry up and finish this talk so I can get back, because they're calling me. You know why? Because it's Recovery Act funds. I mean, you think you live in a goldfish bowl. You don't know what a goldfish bowl is. You can't tell them, what's a university? You know, no. They want to know how many jobs we've already created since we were given the award. So I got to get moving. Yeah. So this is it. As Bob mentioned, it was ranked very high. So I'm told that when Secretary Chu gives talks and he gets to ARPA-E, he's got that slide of the aluminum smelter turning into a battery. And by the transitive property of attention, if this is getting the attention of the secretary. We gotta move at a speed that's uncommon even for a place like MIT. But there's lots to learn. We need cycle performance data. We need to understand how this thing fails. It doesn't fail the way a lithium-ion battery fails. In fact, we can't get it to fail. But I know it's going to fail. I need to know how to optimize the cell, which should be the, what's the optimum geometric ratio, and ultimately we need a cost model. Because that's what people always ask. People in this room, by and large, are going to, oh, that's so cool. I love the electrochemistry. Everybody else sitting there, how much does it cost? That's all they care. They don't care what this is. They just want to know how much does it cost. That's tough. So I'm just going to make a few comments about moving into portable power, and then I'll wrap it up because I want to leave lots of time for questions. So this is controversial. There are a lot of people, mainly people in startup companies that sell lithium batteries, saying, oh, there's no problem, there's boatloads of lithium. But other people don't believe that there are boatloads of lithium. And there's certainly not boatloads of lithium in the 50 United States. It comes from Bolivia, Chile, or from Tsinghua province in China. Now you say, yeah, but price of lithium. And all the projections are based on today's pricing. All right? Now, if you believe the price of lithium is not going to change, okay. Look, I'm not an economist. I'm just telling you what we're doing right now, and you decide whether that's wise. Maybe you're thinking, he's wrong, he doesn't know what he's talking about, the price of lithium is going to fall. Okay? All right? So this is something that we're doing with the MIT Energy Initiative funding. And we want to start looking at redox couples of higher valence. See, what lithium is nice, it's small and it's light, but it's only +1. So for every lithium ion that moves, you call for 1 compensating electron. But what if I took something like aluminum? Every time it moves, I get 3 compensating electrons. Plus, aluminum is a lot cheaper than lithium, and aluminum is found very nicely distributed across the planet, unlike lithium. And also, we don't just want to look at intercalation reactions. That's what we have for lithium-ion battery. The lead-acid battery is not an intercalation battery. It's metathetical. Lead displacement, lead dioxide, back and forth. And that's a surface accumulation reaction. So that's what we're working on in the area of portable power, looking at something that has high valence, so we call it supervalent battery. So it's got to be high valence, greater than 1. Well, 2 is magnesium, that's the obvious one. 3 is aluminum, that's the obvious one. And 4 would be, I wish I could say silicon, but everybody knows silicon's not, it's right smack dab in the middle, it's right on that line. So the next cheapest one, what are the elements? What are the earth abundant elements? What's the earth made of? Well, it's not made of lithium, by the way. Number 1 is oxygen, number 2 is silicon. Number 3 is aluminum. Number 4 is iron. There's more aluminum in the Earth's crust than iron. But aluminum is more expensive than iron because the aluminum-oxygen bond is so tight. And after that, magnesium, titanium. There's lots of it. It's available here in the United States, and it's cheap. Titanium metal is expensive, but we don't need metal. So anyways, that's where I would invite people to think, and that means the electrolyte chemistry too. So let me add these summary remarks, and then we'll close it. So large-scale energy storage, still an unsolved problem. I think the liquid metal battery is a fresh approach. Time will tell if it's scalable. If I had all the answers, I wouldn't be standing here. I'd be so rich I wouldn't have to come to work anymore. So that's, yeah. And the last point that I made, I didn't go into much depth because I didn't want to pack the talk, but I think it's time to look at lithium-free chemistries and be aggressive about it. And by lithium-free, I don't mean sodium. That would be a university approach, wouldn't it? And so I think with that, I'll conclude. Thank you.
Thank you very much, Don. Don's left time for questions, so I'd like to invite questions from the audience.
Are there any new approaches to lead acid? I've read a little bit about people looking at lead acid again.
Yeah, they're trying to, they call them VRLA, voltage regulated lead acid, trying to improve. Lead acid has a very, very low energy density. It's the lowest of the rechargeables. It's 35 watt-hours a kilogram. With the VRLAs, maybe get up to 45, 50. Lithium ion is around 125, 150. But it's, it's like the light bulb problem. If I give you a light bulb that burns 3 times as long at 5 times the price, do you buy it? Not unless it's in a very hard to reach location where you don't want to be climbing that ladder. And that's why people keep going back to lead acid. It's the cheapest chemistry out there. But unfortunately, see, what you want is a current source, right? That's what a battery is. So you want electrons without paying the burden of the protons and the neutrons. And so lithium is attractive because its atomic mass is 7. Lead is, I said, let's go to supervalent. Lead gives you 2 electrons per lead, but the atomic mass of lead is 207. So Mother Nature's really, really nasty. I said, okay, I'll give you 2 electrons, but it's, all those protons and neutrons. So, but it's cheap because lead is cheap and abundant and it's easy to extract. So that's why people keep returning. And it's got its own industrial ecology. It's well in excess of 90%. In fact, I've seen numbers as high as 98% of lead acid batteries are returned for exchange for new batteries. So it's not a case of lead going into the environment and so on. People return their lead acid batteries. And the lead actually gets back into a battery, unlike the soda bottles that we return. They just get shredded and turn into carbon fiber or something because you can't reuse those in the same way. So that's the thing. But yeah, unfortunately, I've got a sort of rule of thumb. If you want to drive a car, a practical car, not something made of monocoque carbon composite with a 90-pound jockey or something like that, but a car with 4 people and groceries and stuff, you need 1 kilowatt-hour per mile of practical driving range, which is why Americans aren't going to buy electric vehicles unless they can get about 200 miles. The knee in the curve is around 200 to 250 miles. Otherwise, it's just sort of a second commuting car, but it doesn't really get around the car ownership. So that means you need 200 watt-hours a kilogram, and lithium ion is around 150. That's why people are now starting to turn to lithium ion, although there are grave safety concerns. Lead acid is down at around 45, 35 watt-hours a kilogram. But when you start looking at price, lead acid is at $100 a kilowatt-hour.
I see more of the grid-scale storage stuff.
Oh, it can't take the currents. There's another problem with lead acid. The problem with lead acid is when you use that battery in your car to start, you drop down about less than 1%. The lead acid battery is sitting at 100% state of charge all the time. And then when you start it and crank it for a few seconds, it goes down less than 1%. If you forget and leave the lights on, or there's one of the doors doesn't close, or you've got some utility running, you don't realize it. If you deep discharge your lead acid battery, you dramatically damage it because you've stripped away all the lead, and then when you go to redeposit it, it's suboptimal. So that it's a log dependence on depth of discharge. So the way you use your laptop or your cell phone battery, you take it almost down to 100% depth of discharge. Lead acid doesn't like to be cycled that way. So people are trying to add surfactants, whatnot, to try to give lead acid the capability of deep level discharge, but that's just not its that's not its calling. So I don't see lead acid making inroads into storage, even though it does have the low price point. Whereas nickel metal hydride, which is what's used in the hybrids today, and lithium ion, they can handle the full depth of discharge, but the price is just out of sight.
Temperature is certainly an enemy of batteries. What does it do to your liquid storage?
It's a
zero temperature, the high temperatures, does it affect it?
Well, you have to be at a temperature above which all the components are liquid. So obviously, when we're working with magnesium, we got to be at 700. So for us, as long as we don't freeze the battery completely, high temperature is It's just the state of the operation. The nice thing about this battery is you don't worry about thermal runaway, which is what you worry about all the time in lithium. And if the lithium battery gets too warm, the electrolyte in the lithium-ion battery is neither acid nor alkaline. It's a non-aqueous liquid. It's a cousin of alcohol. All right. So what happens when you heat? The thing bloats, and so there's all kinds of thermal management. When you're using a cell phone, your face is the cooling fin. Right? Now you build a battery big enough to put 60 kilowatt hours on a car. Well, what's the half width of that battery? It's huge. You can't rely on thermal conduction. You got to have channels, just as you have in the engine block. So you think that's going to drive the cost down? No, it's going to drive the cost up. And you constantly have to worry about thermal runaway. Thermal runaway will cause that battery to bloat. In the extreme, it'll catch fire, explode. It's one thing to have a cell phone, or I'm sure you've seen those loops on the internet of the Dell laptops from 2 summers ago. It was cool because it happened at a conference in Japan. Of course, everybody's got their cell phone. This thing starts bursting into flame, and 5 minutes later, it's on the internet. And but if that happened to a car, that's a different story. So in the case of the liquid metal battery, you want joule heat. Joule heat keeps it at temperature. So it's quite happy.
How do you expect something like a 700 degree C battery to be integrated in a moving vehicle?
Oh, I don't want that. This is only for stationary. No, it's not for moving. I have had the question, how do you expect something like that to go in a home? And I say, this is lower than the combustion temperature inside your furnace. So, and it's a sealed unit. It's going to have 2 leads coming out. So it's not to be put in the living room floor and ask the kids to go and, take it apart,
For the question about stationary, would you comment on the redox flow batteries that use liquid electrode materials?
Sure. The question is about redox flow batteries. These are batteries that they've been around since certainly about the 70s, and the idea is, for those of you who are the chemical engineers in the audience, it's a transport problem. And I mentioned the current density that you can get on an electrode is in some sense limited by the concentration of ions in the electrolyte. And if you draw current, if you call for current too fast, the ions can't diffuse to the electrode fast enough to replenish those that were depleted. So the concept in flow batteries is to use forced convection. So you've got pumps that flow the electrolyte past the electrode, thereby increasing the rate of arrival of ions. And the second piece of it is, to take a page out of our book with the liquid metal, it's a redox couple. So in other words, instead of, again, you want to avoid generating a new phase. So, if I've got liquid ion goes to liquid metal, I pay nothing for that. But if I've got liquid ion goes to solid metal, there's an electrocrystallization penalty there. So in the flow battery, you take something like vanadium and you go from 5+ to 4+, or 5+ to 3+, and it's just ion changes valence, either dumps or takes electrons and then keeps on moving. And then, so at one electrode, you can be reducing, changing the valence, and the other electrode, you can be oxidizing, raising the valence. And people have struggled with these, and they work, but the cost is still too high. The cost is still too high. But, if somebody asked me, should we be pursuing it, I'd say, yeah, let's keep pushing on it. Let's find out if there's some clever way that we can make those work. And, the other idea is that, you've got this big reservoir. You can think of the pools of oxidized and reduced forms of ions as sort of your electrode reservoir. So, anyway.
Can I ask a follow-up?
Yeah.
You alluded to the fact that you were working on other couples.
Mm-hmm.
Are you taking advantage of Gerber and Cedars' work on the survey method that he has?
Yeah.
And I understand why you can't comment on what you might have found. So
Well, some of this, I don't know. MIT has some, there's some IP questions and so on, but
But they're a hopeful alternative.
Oh, yeah. Yeah, what I showed you today was the first thing. And by the way, Garrett Sater was a collaborator, and he and I jointly supervised a Master's of Engineering thesis that started the ball rolling here. So he's been very much involved with this. Yeah.
So has there been any preliminary analysis of failure modes and any results from those?
No. Here's the thing. There are some things that we've learned from the tiny cells, but from what I know in my experience with aluminum smelting, if you make an aluminum cell the size of this soda can, it exhibits all sorts of aberrant behavior that is non-representative of the industrial process. And so our goal is to scale up as quickly as we can, because there's, the surface to volume ratio here is abnormally high. There's all kinds of nonsense that goes on at the external surface that isn't present. If you can imagine this entire front area being flooded, and you have the amount of interface around the perimeter is small, whereas this thing here is starting to become very high. So at the moment, really, the materials limitations that we face, I think, I don't want to trust what we've learned so far about failure modes. Yeah.
Quick two-part question. You referenced how much money has been invested from the government in the battery research. How about by companies, large corporations? And the second piece of that is, do you see much visibility? Do you have much visibility to what some of the Asian economies are doing in this area in terms of investment?
Okay, so first part is, you mean in stationary battery research per se, or in this work here?
In general.
In general? Boy, well, you mean portable and thing? Well, I gave you the total for all of energy. Batteries are starting to come back, but don't forget, starting around mid-90s, our government and governments all over the world abandoned batteries because fuel cells became quite attractive in the eyes of the people making funding decisions. So battery research actually went retrograde starting from the mid-90s and is still suffering from that, because a lot of people who were active in battery research up to the mid-90s who found themselves unemployed or underemployed or had to morph into fuel cell specialists have just said, I'm done with this field. I'm not coming back because I got burned once. So it's only now that things are really starting to roll. As far as the division between portable and stationary, I think the majority has been going into portable because people have had their eye on vehicular applications. I think the portable one, the stationary one rather, is just starting to get attraction. As far as what's going on in Asia, I'm sorry, I haven't really followed it. You better make some decisions here, Bob.
One quick question on the NGK is the limiting factor was the mechanical stability of the membrane. There was no way to just reinforce that. And since mechanical stability seems to be a problem also in lead acid, I would have thought that would have been the easiest part, so to speak, to overcome.
Well, I'll repeat it. The question was if in the sodium sulfur battery it's mechanical stability that is the weak link, then is there no way to reinforce that? And the answer is, as best my knowledge, is no. And the reason is that you've got to remember you've got molten sodium on one side. It's very reactive. The constituents that could possibly give some rigidity have to be stable in contact with molten sodium or molten sulfur and sodium sulfide, and they have to be dielectric, because if they're electronically, so you can't use noble metals because they'll either alloy or they'll sulfidize, and pretty soon you go down the triage and you're left with unobtainium. It's just nothing there. And if you thicken the oxide, your impedance goes up and the current drain is, the limiting current is unacceptably low. My understanding, I think people have really tried on this one. By the way, to the comment about the 700-degree battery, the first electric car I ever drove was the Ford EcoStar, and it was powered by sodium sulfur batteries. So I sat in a car that had about, I don't know, some dozens of these things running at 350 degrees C. So, but ultimately they decided not to go with it. I don't know, in a collision, molten sodium on the highway would just, it'd be bad, very bad. But you don't, go and look at how many people are killed in collisions where the fuel tank explodes. The results of that explosion are far more severe than what would happen if you had liquid sodium. But that doesn't, but everyone in this room will drive a car today. You're fearless. Why? Because you're smart. You're a good driver. So it's okay. It won't happen to you.
One last question.
So how do you envision them being integrated into the grid on a home-by-home basis, but also in a commercial situation like industrial where you might have big demands, and how do you see the charge, discharge, and profile of these batteries?
Well, let's distinguish. I'm talking about the battery chemistry. And so the battery chemistry here lends itself to cycling. But this by itself is not the storage device. In fact, our ARPA-E grant is supporting not only myself but my colleague Steve Lieb in electrical engineering to help with the charge, discharge, all of the electrical engine, because this battery operates with a cell voltage of about 1 volt. But I mean, you need to get to, and it's DC. So all of the systems integration involves the use of the appropriate electrical engineering hardware. And you can't go to Radio Shack and buy a charger for this thing. So that's all part and parcel of it. And as far as the integration into the grid, that's going to involve all of this other hardware. We're focusing on giving the core technology, which is a cell that can store charge at a very, very high current rate and give it back on demand with a long lifetime and low cost. But you're absolutely right. I mean, this is a long way from something that will cycle like this and even serve the purposes of a single-family home. So we got to get to work.
In the efforts of not running too far over, I think we ought to stop here, but let's thank Don one more time for a very Thank you all for coming, and enjoy Energy Futures Week.